This is a talk about testing what's called the linear no threshold theory for radiation-inducing cancer. This is Dr. Polycove tomorrow will give an additional discussion of this. Let me just say what the problem is. It's well known that high doses of radiation cause an increased risk of cancer. So there are a lot of reasonably accurate data points up here at high dose of what the cancer risk is. But practically all practical applications of radiation deal with doses down in this range. So the question is, what is the risk of cancer from these low doses of radiation, that is from low-level radiation? Well, the way it's been done is you just draw a straight line from here down to the origin, and you assume then that the risk from this dose is just this risk here. In other words, if you get 1% as much radiation, you have 1% of the risk of cancer. Now, this is a very important assumption, this linear no threshold assumption. For example, the problems would disappear if low-level radiation is not harmful. All the precautions people take with diagnostic X-rays, and this often degrades medical effectiveness. A lot of people are afraid to get X-rays because they're afraid of the radiation will cause them cancer. But this is low-level radiation down in the region we're talking about. Radioactive waste after burial it's difficult to conceive of how anybody can ever get a high dose of radiation. All the things that people claim they worry about, and even that's not a legitimate worry, but that's another topic. These are the things that give millions and hundreds of billions of people, because you're adding up over millions of years, doses such that they might have one chance in a billion of getting cancer. So this is very low dose radiation that people are worried about. Even nuclear reactor accidents, which people think you might think would give high doses, practically all the deaths that people calculate would result from nuclear reactor accident come from low-level radiation. All the future radiation from the Chernobyl accident, there's all these estimates that there will be like 20,000 people will die from the Chernobyl accident eventually. All that's due to low-level radiation. So if low-level radiation isn't dangerous, you can forget about them dying.
What is LNT?
Linear no threshold. I'll be using it all through, and then Dr. Polycove tomorrow again, so maybe try to remember that one. In making these transparencies in a computer, you got to be careful of the number of letters you put in a line. I mean, you can't squeeze them together or anything like that, like on handwritten ones. All the cleanup of government installations, like at Hanford, where they're projecting $150 billion, not million, $1 billion to clean up the residual radioactivity. Also, other government installations costing many, many hundreds of billions of dollars. All that money is wasted if low-level radiation isn't dangerous. Routine emissions from nuclear plants. This is costing, well, I don't know, certainly hundreds of millions of dollars, if not billions. Fallout from bomb testing, which actually was instrumental in an election at one time, in a presidential election at one time, would not be important. But probably the most important thing is a carryover to chemical carcinogens, because if it's found that linear no threshold doesn't apply in radiation, it would probably collapse in discussing cancer-causing chemicals. The basis for this linear no threshold theory is all theoretical. As I say, as Dr. Polycove especially will say, and I'll point out, there's no experimental basis for assuming that low-level radiation causes excess cancer. Well, the basis is that it's sort of well understood, or generally believed that a single particle of radiation hitting a single DNA molecule in a single cell nucleus in our bodies can initiate a cancer. Well, according to that, then, the number of cancers that are initiated is just proportional to the number of hits, and that's just proportional to the number of particles of radiation, and that's just proportional to the dose. So therefore, the number of cancers initiated by radiation is definitely then proportional to the dose. The problem is that this does not consider biological defense mechanisms. Now, to show that this is a problem and that this simple theory is a problem, the number of spontaneous DNA lesions in each cell in our bodies occurring due to random effects of thermal motion of the electrons and so forth, chemical attacks from free radicals. Anyhow, all these things are going on. They cause 10,000 DNA lesions in each cell in our body every hour, or 70 million in a year. Well, the number of these DNA lesions to each cell from a reasonably large dose of radiation here is something like 10 to 20, possibly up to 100. But whatever it is, certainly, and these spontaneous and radiation-induced lesions are indistinguishable. So, therefore, the radiation initiating cancer is a trivial effect. If you're getting 70 million a year, what harm can an extra 100 do to you? I mean, that can't cause any problem at all. How then can radiation affect the cancer risk? The only possible answer is that radiation affects these biological defense mechanisms. So it's not because radiation initiates cancers that you have a risk, but rather because radiation, high levels of radiation, reduce these biological defense mechanisms. But then there's no reason to expect a linear relationship for the biological defense mechanisms as there was for initiations. It's easily possible that low-dose radiation may even improve might even improve biological defense mechanisms, while high doses reduce biological defense mechanisms. And there's actually a lot of evidence for this. Dr. Polikov tomorrow will give more of it, but let me just introduce some things. One sort of genetic damage that people can measure are chromosome aberrations. And here are just a couple of experiments. These are experiments where there are large doses of radiation are found to cause chromosome aberrations. However, if you precede these large doses of radiation with a low-dose radiation a few hours before, what's this one, 6 hours before, you get far fewer chromosome aberrations. Here's another example here. If you just give the high-dose radiation, you get this many. If you precede it with a low-dose radiation a few hours before, you see you get far fewer chromosome aberrations. This is an in vitro experiment. Here's an in vivo. These are in mice. And here you see that in two different things, if you precede the high-dose radiation with low-dose radiation, you substantially reduce the number of chromosome aberrations. Those are two experiments, and there are a whole bunch of these. This is a list I compiled a couple years ago of various other experiments where this was shown, or it was shown that low-dose pre-exposure reduces chromosome aberrations from later high-dose exposure. So this is not a debatable question. This is well recognized. So here's a clear case where low-dose radiation improves biological defense mechanisms rather than reducing them. Another type of damage that can be detected by experimental techniques is genetic mutations. And here's a case where if you give a high dose of radiation, you get this many genetic mutations at this particular locus on a gene. But if you precede it with a low dose of radiation, you reduce the number of mutations very substantially. This is the one that I think appeals to me most. You probably all know about the famous experiments of Muller on fruit flies, Drosophila, back in the 1920s that got a Nobel Prize. This was the first demonstration that radiation can cause genetic defects. Muller left out part of the experiment. He gave these fruit flies large doses of radiation and found that they had increased genetic defects in their progeny, in their offspring. However, if he had gone one step further and given them a low dose of radiation ahead of time, there would have been far fewer genetic defects in their progeny. So in other words, the low dose radiation actually improves these biological defense mechanisms and is protective against cancer. There are lots of other experiments like that. I'll leave that to tomorrow. Another thing is effects on the immune system, which can be measured. There's now abundant evidence that immune system plays an important role in opposing cancer development. In fact, NIH has a big program of trying to cure cancer, and they've even claimed some cures by improving the immune response. Well, what does low-dose radiation do to the immune response? Well, these are 5 different methods of measures of immune response, and you see these are all on the basis with no radiation. It would be 100. The immune response measured by these methods would be 100, and if you give low doses of radiation in increasing amounts, it stimulates the immune system in all cases here. So here's another indication then that low-dose radiation stimulates biological defense mechanisms. Well, the conclusion is that low-level radiation stimulates biological defense mechanisms against genetic damage. There are lots of mechanisms for this have been suggested, but Dr. Polikov tomorrow will discuss those. So the theoretical basis for the linear no threshold theory is out the window. I mean, it can't be because, the original theoretical basis was that radiation initiates cancers, but the initiation of cancers by radiation is trivial. It adds a trivial amount to the cancer initiations that are going on all the time in our bodies. The only way radiation can affect cancer risk is by reducing biological defense mechanisms. But far from reducing biological defense mechanisms, all this evidence I've been showing indicates that radiation improves biological defense mechanisms. That can't be the other way. And these are not controversial things, I should say. Now, for experimental evidence, Dr. Polikov tomorrow will give a much fuller discussion of these, but one thing that he won't cover, I thought I had a transparency of here. I'm purposely covering this because he'll cover it. These are these radium dial painters. These are women who painted radium on watch dials to make them glow in the dark, and a lot of them got bone cancer. Well, these are the data on them. This is tumor incidence against radiation dose here, and these are the data points, except I've magnified this part here and down here, and this last point is this one here. Below that, 0, 0, 0, 0, nothing. And all these women, there were no extra, no bone tumors at all. And you see that the statistics of this are enough to say that anything like even this curve that I've shown here would not be defensible in light of these data. So, and then Dr. Polikov will show a lot more data tomorrow on this along these lines. In other words, that experimentally, there are no experiments that confirm the linear no threshold theory in the low dose region, and there are a substantial amount of data which go the other way, say that low dose radiation does not cause cancer. Well, the rest of my talk now will be about my own work on this, which is another example of an experimental test of this linear no threshold theory in the low dose region. I got into the business of measuring radon levels in homes, and we gathered data on it. I have a big compilation of data on radon levels in homes. And as a result of this work, I was able to determine or estimate, as a more fair thing to say, the average radon level in various counties in the United States. This was 1,729 counties, which comprise 90% of the U.S. population. So this is a real, the statistics are of no concern here. I mean, there's such good statistics. Now, if I'd plot these 1,700 points on a graph here, you'd see nothing but black, not to mention the labor of plotting all those points. So what I've done to make it more visible is I've divided the radon level in counties into ranges. So, for example, between 3/4 of a picocurie per liter and 1 picocurie per liter, there are 216 counties in the United States that have radon levels in that range. And for these, the average lung cancer mortality rate was this number, 66 times 10 to the minus 5 per year, with this very small standard deviation of the mean. When you have over 200 data points, you're going to get a very small standard deviation of the mean. 3/4 of these counties were below 72, and 3/4 were above 58. That's what these points show. Well, then you do this for all the other radon levels along here, and I just connected the points, and you see that there's a very strong tendency for lung cancer mortality to go down as radon levels go up. This is a very strange thing. I mean, the theory says that radon causes lung cancer, so therefore it ought to go up like this. All other things being equal, the more radon, the more lung cancer with this slope here. So this is a very surprising finding. I was very surprised when I found it. But of course, this doesn't prove anything. Maybe these counties out here have a lot less smoking, and these counties have a lot more smoking, something like that. So these are things that have to be looked into, or maybe these counties have more poor people, and poor people get more lung cancer for other reasons. So there's this is the beginning of the study. Well, the one thing people worried about, and originally they say, people don't spend their whole life and receive all their radon exposure in their county of residence at time of death, where their cause of death is recorded, which goes into the mortality rate statistics. Well, the solution to this is rather simple. You just correct the theory for this problem, and all our comparisons with theory include this correction. Now, it helps here if you reduce the retirement states of Florida, California, and Arizona, because these are areas where a lot of people go to retire and they die there, and their cause of death is recorded in those states, whereas their main radon exposure was obtained somewhere else. So it makes the study cleaner. If we take those states out of our study, that still leaves 1,600 counties, which is plenty. But whether you include these 3 states or not, the results are essentially the same. Now, a more serious problem is what epidemiologists call the ecological fallacy. Epidemiology uses a risk versus dose to individuals. That is, they want to know how much dose each person got and did he or didn't he get cancer. Whereas our data is the average risk versus the average dose to groups of individuals, namely the populations of counties. So this raises an important problem. which epidemiologists are very justified in worrying about. For example, suppose the risk for cancer behaved this way. This is the way a lot of risk versus dose curves go. In other words, they basically have a threshold. Say if it had a threshold at 50 here, now suppose you have different counties had average radon levels here or here. Well, that doesn't tell you how many people they have that were above this threshold. So therefore, the average dose does not determine the average risk. And assuming that it does is what's called the ecological fallacy. However, underlined but, in a linear theory, in a linear no threshold theory, this does not apply. The average dose does determine the average risk. In other words, this is in a linear no threshold theory, you don't have a threshold, and it turns out it doesn't matter whether you have how many people you have here or how many people you have here. Only the average dose determines the average risk. This may be familiar to some of you from the fact that the population exposure expressed as man-rem or person-rem can be used to calculate the number of deaths. All that's based on the linear no threshold theory. Now, we want to say, so in other words, that the ecological fallacy does not apply in our study. Now, this is the only transparency I have that has a little bit, looks like mathematics on it. So if you don't want to look at it, you can sort of close your eyes for a second. Let M prime be the mortality risk to an individual, and R prime be his radon exposure. Well, then you have the risk to various individuals. It's different if you're a smoker or non-smoker, according to accepted theories, where these things, A sub n is for non-smokers, A sub s is for smokers, and B is the additional risk from radon. They're obtained from, they're known constants obtained from high dose. The B is obtained from high dose data, and these are just obtained from the general population. Well, if you just add up these numbers for all the people in a county, all the residents in a county, and divide by the population, well, if you add up the risk to all the individuals and divide by the population, you get the average mortality rate. If you add up the radon exposures to each individual and divide by the population, you get the average radon exposure, and then in adding these things up, you get this term, which depends on the fraction of the population that are smokers, and this is the fraction of the population that are non-smokers. So this is straightforward mathematics here, which starts with a study of individuals and comes out with the thing that our data are measuring, namely the mortality rate in the county versus the average radon level in the county. And you have this factor in here, which I call M0. So if you divide the mortality rate in the county by this M0, you get the lung cancer rate corrected for smoking. And so this is the quantity which we'll be discussing then as a correction for smoking. You notice that this is all done with rigorous mathematics and there's no problem with the ecological fallacy. We started from a study of individuals, and we get that result with rigorous mathematics. Well, then this is the data I showed before, lung cancer rate versus radon exposure. This is for males that I showed before, and this is for females, which is pretty much the same. Well, if you correct for smoking, that is divided by this M0, then you get these curves, which you'd have to look awful hard to see any difference between these and these. So in other words, the fact that smoking does not explain, at least at first sight, smoking cannot explain this discrepancy with theory. In particular, what we do is we plot M over M0, we say is a linear function of the radon exposure. According to the theory, this slope of this radon dependence should increase at a rate of 7.3% per picocurie per liter of radon. Whereas, in other words, it should increase at 7.3% per unit radon exposure. If you fit the data, you get something which decreases with increasing radon exposure. For males, minus 7.3, for females, minus 8.3, with these very small standard deviations. You see that this number is discrepant with this number by more than 20 standard deviations. And in statistics, anything that's off by 20 standard deviations is just out of this world. The probability of this occurring by chance is roughly equal to the total numbers of electrons, protons, and neutrons in the entire universe. Anyhow, just to be sure everybody understands, the lung cancer, according to the theory, the lung cancer rate should increase with increasing radon exposure with a definite slope, and this slope is determined from data on minors, which is obtained at high levels of radon. Whereas the data that we find has this negative slope of minus 8% per picocurie per liter, average between males and females. The theory gives a positive slope, the data gives a negative slope, the discrepancy is more than 20 standard deviations. Now, as I say, we did nothing to cause this discrepancy. It came as a big surprise to me. It just appeared in the earliest data, and as more and more data came in, the discrepancy became worse, and the statistical significance kept becoming stronger. And this is what I call our discrepancy. So the rest of this talk is about my efforts to understand this discrepancy without abandoning this linear no threshold theory. Well, potential explanations for our discrepancy. The first thing might be errors in our radon data, that is the average radon level in various counties. However, we now have 3 independent data sets, and they all give the same results. There are measurements, 272,000 measurements, which gave the average radon level in 1,151 counties. EPA completely independently did 40,000 measurements, which gives the average radon level in 1,075 counties. And then there are various state-sponsored measurements which give average radon levels in 358 counties. You can analyze either of these, any one of these 3 sets separately, independent of the others. You get essentially the same results. And if you correlate the radon levels in counties obtained from the different studies, they correlate very well. So I'm convinced then that it can't be errors in the radon data. Now, the next thing would be, what about errors in our smoking prevalence, which we call S, that is a fraction of the population that are smokers. We use 3 different data sources, and all give roughly the same results. But suppose we're wrong on all 3 of them. I said, how strong a negative correlation between smoking prevalence and radon can explain the discrepancy? I call this core R, the correlation coefficient between radon levels and the prevalence of smoking in a county. Now, what I did here was take all the smoking levels in counties and all the radon levels in counties and reassign the smoking levels. Assume that the county with the highest radon level had the lowest smoking prevalence. The county with the next highest radon level had the next lowest. And all the way through our 1,601 counties until the county with the lowest radon level had the highest smoking prevalence. Even this only explained half of our discrepancy. So that's looked pretty bad. However, it turns out if you assume that the width of the smoking distribution, then not only don't we know which counties have higher and lower smoking, but the width of the distribution of smoking prevalences was much wider than our best estimates. Well, then you can explain a discrepancy if you assume an almost perfect correlation between radon and smoking. That is, assume that the highest radon counties have the least smoking and the lowest radon counties have the most smoking, with an almost perfect correlation. The correlation would have to be minus 0.91. So the question is, how credible is this correlation, such a high correlation, this minus 0.91? Now, there's no direct causal relationship between smoking prevalence and radon exposure. I mean, smoking doesn't cause radon or anything like that. So the most likely source of a correlation between them is through socioeconomic variables, which I call SEV. It's another thing you got to remember for the next couple minutes. SEV means socioeconomic variables. Well, we considered 54 socioeconomic variables, and I'll show you a list of them pretty soon. Of all these 54, the largest correlation with radon was 0.37. Remember, we need 0.91 to explain the discrepancy. The next largest of the 54 was 0.30, and 49 of the 54 had less than 0.23. Now, the S values that we use actually had a correlation of minus 0.28. In other words, that's about as large a correlation as can be reasonably expected. And the S values from our alternative sources had even lower correlations with radon. So it seems to me then that this correlation that's required here of 0.91 is just completely implausible, since socioeconomic variables don't correlate with radon. This is a list of the socioeconomic variables we used: total population, population density, rate of population increase, percent in urban areas, percent white, male to female ratio, age distributions, things like the physicians per capita, hospital beds per capita, money spent on education, the percent of high school graduates, percent of college graduates, housing variables, economic variables, dollars per capita income, things like that. And incidentally, I'm now expanding the study into another couple of hundred of socioeconomic variables, if that convinces anybody. Okay, so now the next possible explanation would be direct confounding by socioeconomic variables. Maybe there's some socioeconomic variable which is somehow related to radon by chance. And there, for example, let me use it, instead of going through it the way it's written here, let's talk about income. So maybe rich people have lower lung cancer, and rich people, for a completely different reason, have higher radon levels. Then that would be, income would be a confounding factor here. Well, in order to treat this, I assume that I divide our counties, our 1,600 counties, into 5 groups according to their income. That is, the 20% with the highest income are 1 quintile, the 20% with the next higher income are the 2nd quintile, and so on down to the 20% with the lowest income would be our 5th quintile. Then we call those strata. Now, each of these strata has roughly the same value of the confound, would have roughly the same income. That is, the 20%, the richest people would have more or less the same income. The 20% poorest would have more or less. The 20% in the middle stratum would have more or less the same income, and so on. So, therefore, if you analyze each stratum by itself, that is, plot the lung cancer rate versus radon level for each of these stratum, that ought to be free of confounding by income. So then if you average the slope you obtain from each of these separate analyses, you get a value of the slope which is free of confounding by income. Now, income is just one of our 54 socioeconomic variables. We did this. We studied our 54 socioeconomic variables, divided each one into 5 strata, for both males and females. That means we did 540 different analyses here. All 540 of these slopes were negative, and there was no strong trend which made it look like, say, one of our socioeconomic variables was doing anything here. If you average over the 5 strata, you always got a slope very similar to this slope we get for the entire data set. So the conclusion is that no individual socioeconomic variable can be an important confounding factor, and also nothing that is strongly correlated with a socioeconomic variable can be an important confounding factor. For example, air pollution was not one of our confounding factors. However, air pollution correlates with things like amount of manufacturing, with a population density, things like that. So therefore, air pollution has to be excluded here. Another view of these conclusion of this analysis is that the slope of lung cancer rate versus radon levels are negative and large if we consider only the very urban counties, or if we consider only the very rural counties, if we consider only the wealthiest counties, or if we consider only the poorest counties, if we consider only the best educated counties, or if we consider only the least educated counties, if we consider only the counties with the best medical care, or only counties with the poorest medical care, and so forth through our 54 socioeconomic variables. And it's also true for all the straight in between. For example, if we consider only counties with average wealth, or if we consider only counties with average education, only counties with average medical care, and so forth, you always get the same behavior where lung cancer rates go down as radon levels go up, at approximately the same rate, in fact. Now, another thing we did here, another possible explanation was maybe there's something more complicated going on. So I picked out the problems of confounding that have the largest known effects. In other words, we know quite a lot about radon. We did lots of studies of radon, how it relates to all sorts of house characteristics and socioeconomic characteristics and so forth. The biggest problem we could come up with there was that urban homes average 25% less radon than rural homes, and also urban people smoke about 24% more frequently than rural people. Well, there's a made-to-order confounding factor here. That's what I call the urban-rural effect. Now, another thing is houses of smokers average about 10% less radon than houses of non-smokers. This came out of our studies. I can't explain it. It's as though smokers open their windows more to keep out the odors, and that reduces the amount of radon, something like that. But anyhow, so but these things, since I know exactly what we have here, I could calculate these things in great detail, and it turns out that these effects explain about 3% of our discrepancy. And these are typical of the largest expected effects of any confounders. I can't imagine a confounder would be more made to order to cause trouble in our study. See, another thing I did here was I asked, is there some unrecognized reason, maybe I'm missing something, why there's some strong correlation between cancer mortality rate and radon, such as we find for lung cancer, which just comes about for reasons I don't understand. Well, in order to do this, I did the same study for all the other types of cancer. There's 33 other cancer sites, well, 32 other. And I determined the cancer rate versus radon level, and also the double correlation of cancer rate versus radon level and smoking prevalence for for each one of these 33 principal cancer sites. For no other cancer type except lung cancer was the MR correlation anywhere near as strong. And for lung cancer, The correlation between cancer rate and smoking was positive. That is, more smoking, more lung cancer, as expected, and very strong as expected. The correlation between cancer rate and radon was very strong as expected. In fact, pretty near as strong as it was with smoking. I mean, not a factor of 2 different, in fact. However, the sign of the correlation between lung cancer rate and radon was negative, contrary to expectations from the theory. In other words, lung cancer is very unique here. No other type of cancer has anywhere near this kind of behavior. Well, we did a lot of other tests, which I won't bore you with here. Confounding by combinations of socioeconomic variables. This can explain very little of our discrepancy, maybe 15% of our discrepancy, giving it everything. Confounding by geography, that is, if you just look at one part of the country at a time, do the whole study just for individual parts of the country. The results were very similar for each region of the country, and even if you go down to individual states, if you just look at the individual states and look at the lung cancer rate versus radon in that state, you generally get a negative correlation, and if you average this for all the states, you get something very close to what we got for the country as a whole. Of course, there's a lot more statistical variation if you only have 25 counties than if you have 1,600 counties. Confounding by altitude and weather, we found the results were similar whether you're talking about only the highest altitude counties, which would have the lowest barometric pressure, or only the sea level counties. If you considered only the counties with the most rainfall, or only the counties with the least rainfall, or the counties with the most days per year of rainfall, or the counties with the least days per year of rainfall. The counties with the highest winter temperature and the counties with the lowest winter temperature. Counties with the highest summer temperature, only counties with the lowest winter temperature, summer temperature. Counties with the most sunny days per year, the counties with the least sunny days per year. Also wind, the counties with the highest average wind and counties with the lowest average wind. Or, of course, counties, the average of all these too. They all had the same behavior. The higher the radon level, the lower the lung cancer rate. Discarding outlying data, we did lots of tests of this. It always made the discrepancy worse, so we didn't discard anything. There are a lot of problems with ecological studies which are discussed in the literature. I have some transparencies on that. There's a question, does the discrepancy depend on the Beer 4 model used here? And no, we showed it's good for any other linear no threshold model. Well, this stage I thought I'd go beyond this linear fit to the data. Remember, the data weren't really fit by this straight line very well. The straight line just shows this negative trend. However, you see that it's more like a curve than a straight line. So I went to the next step and fitted it with a linear plus a quadratic. That is, assume that the lung cancer rate corrected for smoking is proportional to a term in the radon level plus a term in the radon level squared. And there you get a very nice fits to the data. And I call these, this is for males and this is for females, and I call these our standard curves. And the next few transparencies will all have these standard curves on them. I'm not going to adjust those standard curves. I'm just going to show the data and show the standard curves. Well, this is income per capita. These are the poorest counties, these are the richest counties, and these are the median, average income counties. And you see that there are some differences here. The poorest counties seem to have less lung cancer. The richest counties seem to have more lung cancer. But each one follows the shape of the standard curve quite well. That is, if you move the standard curve up or down a little bit, it would fit the shape here. So the shape seems to be independent of this matter of income. This is physicians per capita, the same sort of thing. The counties with the highest number of physicians per capita seem to have more lung cancers, at least more lung cancers diagnosed. Counties with the lowest physicians per capita have fewer lung cancers, but still it follows these curves very well. I shouldn't have used this among physicians. This is the percent of earnings from farming. So this is an indication of this urban-rural effect I was talking about before. You see, counties with the least farming, these would be the urban counties, have much lower radon levels than the rural counties with a lot of farming. And in fact, you see that the urban counties do have higher lung cancer rates. The rural counties have lower lung cancer rates. But once again, if you move these standard curves up or down, they would fit very well with the data. The data shows the same trends, whether you're talking about urban counties which have low radon, or if you're talking only about rural counties which have high radon, they still follow these same curves. This is smoking prevalence. And you see there is this correlation between smoking and radon. The counties with the least smoking do have higher radon levels on an average. But of course that's corrected for when we take out this M over M0. The M0 corrects for smoking. And the counties with the most smoking do have lower radon levels. But still, if you just consider those counties alone, you get this very nice fit to the standard curves. Now this is for different sections of the country. This is northeast, north central, south, and west. This is the Census Bureau's division of the country into 4 regions. You see that the northeast has a lot more lung cancer. The west has less. But again, for each region alone, if you move these standard curves up, you get a pretty good fit to the data in all cases here. Another problem that came up was, this was brought up by an epidemiologist, said people living in apartment buildings are underrepresented in the surveys, and these have lower than average radon exposure. And there's good reasons for that, but here's my analysis of the problem. I let HA be the percent of housing in buildings with more than 4 units. And incidentally, I'm extending this now to up to 50 units, 50 housing units in a building. I haven't done the analysis yet. I can't believe it's going to turn out different. If you assume that none of the people living in apartment buildings are included in the radon surveys, and all of them have 0 radon exposure. That's about as far as you can go here. The result is that the slope of the line has changed from minus 7.3 to minus 7.1 for males, and from minus 8.3 to minus 8.4 for females. So it doesn't make any difference at all. Another thing is, if you delete counties with the highest fraction of people living in apartments, you don't get anything very different either. Well, I spent some time trying to think, suppose there's some unknown confounding factor that I'm missing here. Not a socioeconomic variable, not a weather factor, the ones I've studied, maybe something entirely different that I'm missing. And now, of course, an unknown confounder can screw up any epidemiological study. This goes, so if people are going to say, how do you know you didn't get all the confounding factors? You can apply that to any epidemiology study that's ever been done. However, I did some thinking about what would be the requirements on this unknown confounder. We'd have to have a very strong positive correlation with lung cancer, comparable to the correlation of smoking with lung cancer. And this means it increased 50-fold from 1920 to 1990, because that's what lung cancer did. It increased in males mostly from 1920 to 1960, and in females mostly from 1960 to 1990. And that's asking a lot of a confounding factor to do all that. And also at the same time, even if it did all that, it would still have to have a very strong negative correlation with radon, much stronger than the correlation of any of our 54 socioeconomic variables. Then it would have to be applicable to each socioeconomic stratum, applicable in each geographic region, and so forth. It just seems much more credible to me that the linear no threshold theory fails in this dose region under study, where there's no experimental evidence supporting it. I did pay a lot of attention to problems with ecological studies here. There is a substantial literature on this, aside from the ecological fallacy. The most important one is what's called nonlinearity of confounding effects. It's sort of like the ecological study applied to confounding factors. The point is that confounding factors are not well represented by county averages. For example, when you treat the average income as a confounding factor, that isn't quite completely, doesn't quite tell you a whole picture. Maybe the effects depend on the fraction that are poor or the fraction that are rich, something like that. Well, so to get around this, I used several different confounding effects for income. I used average income, median income, percent below poverty level, percent unemployment, and in my new extension I have several other measures of economic status. Then differing age distribution, this was brought up, differing age distributions in counties. Now, of course, we use age-adjusted lung cancer rates, and we included as possible confounders the percent that are aged greater than 74, percent that are aged greater than 64, the percent that are aged 5 to 17, and the birth rates, which are roughly related to the percent age 0 to 5. So we cover a lot of that. Again, in my new studies, I'm going to cover a lot more of that. There are several other problems with ecological study, which I won't go through here, but none of these apply to our study. I think there's nothing controversial about that statement, I don't think. Now, what about reactions to our study? There's been a lot of positive reactions. I've had invited papers at annual national meetings of Health Physics Society, Society of Nuclear Medicine, American College of Nuclear Physicians, American Association of Physicists in Medicine, American Physical Society, American Chemical Society, 2 different years, American Nuclear Society, 2 different years, Royal Society, necessarily American Nuclear Society gave me a special award for this, Royal Society of Canada, Canadian Nuclear Society, the Israel Nuclear Society, and this organization here. Had invited papers at conferences overseas in France, Japan, twice, Hungary, the Netherlands. Many talks at other meetings, seminars, colloquias, universities, laboratories, and stuff like that. Testimony at hearings on this. Lots of invited publications of abbreviated versions in journals and books. So it's gotten a lot of attention around the world. However, the reactions from the official organization, this is the National Council on Radiation Protection and Measurements, this is the International Commission on Radiological Protection, this is the National Academy of Sciences Committee on Biological Effects of Ionizing Radiation. They've just ignored it. And it's not that it hasn't been called to their attention, believe me. I've asked them about what they're doing about it. I've offered to help them. I've offered to come visit them at my own expense and discuss things with them. I've given them made my data available to them, all my data, let them analyze it, or I said I'll do any analysis they suggest, anything they suggest. Everything's been ignored. On the other hand, they don't ignore it in bad-mouthing it to other people. When friends of mine ask them about it, they say, oh, there's this wrong with it. I'll mention a few things that they say later. And they, I can't read this, they just don't want to discuss it. And most of their objections are clear to me that they didn't read our paper. In fact, one of them admitted, I think there were two of them at separate occasions, admitted that they didn't read the paper because it wasn't worth reading. Now, my understanding of the problem is that these are all epidemiologists I'm talking about, and my understanding of the problem is that epidemiology is a technology rather than a science. Our study doesn't fit into their technology. I mean, they don't do things like testing a linear no threshold theory. What they do is try to find out, does radiation cause does radon cause lung cancer? And they don't care about the theory when they do that. And my feeling is that they don't understand the scientific method. So I have to put in something about the scientific method here. The scientific method is understood by physicists, I mean, I'm basically a physicist, is that if the predictions of a theory are contrary to experimental data, and if there's no plausible explanation can be offered for this discrepancy, if no other data contradict these data or if there's no other data that support the theory in the same region, the theory cannot be accepted in that region. Based on this principle, theories are constantly being modified or abandoned in many areas of science. I can give lots of examples of this. In my earlier years, I was a nuclear physicist trying to understand the motion of the neutrons and protons in the nucleus. Well, when I had my first course in this given by Professor Seitz, who comes to these meetings, I was hoping he'd be here, he taught us that neutrons and protons in the nucleus are entirely different than electrons and atoms. Electrons and atoms go around in orbits. They go around their orbits many times before anything happens, whereas neutrons and protons in the nucleus are constantly bumping into one another. They can't have anything that resembles an orbit. And there was lots of good data supporting this, but then some new data came along which seemed to indicate the other way, that neutrons and protons and nuclei do go around in orbits. And this caused a great change. People just dropped the old theory and started working, gathering new data, and the new theory kept holding up further. And there were some other new developments I could tell you about. And by the 1960s, it was generally understood that we understand the motion of neutrons and protons and nuclei better than we understand the motion of electrons and atoms. And that's going a long way because, you know, every grade school kid can tell you all about the motion of electrons and atoms. Anybody who's ever been to a planetarium knows about that. Well, anyhow, so at least in physics, when a theory doesn't hold up to experimental data, you got to change the theory. You can't keep using that theory. Well, with the linear no threshold theory of radiation carcinogenesis, as I've been showing, doesn't hold up to, and as Dr. Polikov will show more tomorrow, doesn't hold up to experimental tests, but yet it continues to be accepted and used by all official and governmental organizations. If I sound bitter, of course, after the last speaker, I guess I have nothing to complain about.
Just had 4 years.
Well, I've been teaching a course in his stuff too, and my section on DDT really gets me pretty hot too. The only thing is, my understanding is that DDT wasn't banned because of the scientific studies. Ruckelshaus admitted that he banned it for political reasons. And that even aggravates me more. But anyhow, let's get back to this. One of the first things these people, these bad mouthers say is, we didn't adequately control for smoking. I've already told you what we do for smoking, showing that even a perfect correlation doesn't do the job, and that there's no reason to expect anything like a perfect correlation between radon and smoking. But then there's a question of the sensitivity of our results to smoking prevalence as compared to average radon exposure. It turns out that smoking isn't such a completely dominant factor here. It's true that smoking is a much more important cause of lung cancer, according to the usual theory, than radon is. However, smoking doesn't vary that much from one area to another. The variation of the distribution of smoking prevalences in counties is only about 13% of the mean, which corresponds to 11.3% in variation of lung cancer rates among counties. On the other hand, the distribution of radon levels in counties is very wide. Something like, anyhow, it turns out that smoking is less than twice as sensitive as radon to determining lung cancer rates in counties. I just have two more that three more maybe I can hit. One of the excuses people have given for not looking at our study is they say they read our 1990 paper, which had a lot of weaknesses, which were laid out in that paper, and all they were doing was agreeing that the things I said weren't very complete, were not complete. But the conclusions, as stated in the publications, in the 1990 paper, I said this discrepancy was interesting and should be investigated, whereas our 1995 paper concluded that linear no threshold theory fails. To give you my personal reactions, in 1990, I spent $1,500 to reduce the radon level in my home. In other words, I didn't believe it. I mean, look, it was interesting, but I really didn't believe it. In 1995, I switched the system off to save electricity. Certainly, along the lines of the previous speaker here, trying to get attention from the media, I have an offer out to eat plutonium, which everybody says is, or inhale plutonium. And I made this offer in all seriousness, and I just can't get any attention from media people to it. And it seems to me that would be a big story for them, wouldn't it? I mean, they don't want it. But there's an easy, for people who doubt the credibility of our study, there is an easy answer, which I've offered. All that someone has to do is suggest a potential plausible explanation for our discrepancy. I'll calculate what numerical values of that explanation are successful in explaining it. And if the results are not implausible, I will concede. And my offer now is up to $2,500. And this has been offered through email discussion groups. I've tried to get it published in journals, but they won't accept it. And to show that, and incidentally, the question is, if it's not, the judge of plausibility is up to them. In other words, if they can get any prominent scientist to say that they think their explanation is plausible and is willing to have their name published in my rebuttal letter, my rebuttal paper, they get their $2,500. So they make the judgment on the plausibility. To show that this procedure is not unreasonable, I offer to provide not implausible explanations for any finding in any other ecological study. Ecological studies in general are not a good way to determine the cause-effect relationship. It's only to test the linear no threshold theory that it happens to be good, but these people just don't understand that. Anyhow, if anybody has any other proposals on how to test the credibility of our discrepancy, they're always welcome. But the one thing I can't stand is ignoring it. And if I sound frustrated, I join the previous speaker in frustration. Thank you.